Good day everyone, this is CVE167 Pre-Stressed Concrete Design Module 2 Stresses in Pre-Stressed Members. So welcome to the second module of this course. So for this lesson, we will be discussing what are the stresses present in a pre-stressed member. So by the end of this module, you should be able to first determine stresses in a pre-stressed member, and then understand basic principles of pre-stressed concrete. So the codes of practice. So there are different codes of practice depende sa um, um, country, but sa Philippines, they all have something in common. So the codes of practice limit the allowable stresses in pre-stressed concrete. So that's why it's called allowable kasi there are limitations. So there are minimum value, maximum value, allowable value. So yun yung dahilan bakit tayo may sinusunod na mga codes like building codes, yung mga design codes natin. So most of the work of the pre-stressed concrete design involves ensuring that the stresses in the concrete are within the permissible limits. So there are many factors why we should design a concrete member within the permissible limits. No? So first is efficiency, economy, and then yung um, structural integrity ng concrete. So since we deal with allowable stresses, so only service loading is used. So yan yung mga live load, dead load, so yan yung mga additional. So yung other loads hindi na siya kasali, like mga wind load, earthquake load, so hindi na siya kasali dito sa design ng pre-stressed concrete. So for a service load na case, at any section in a member, there are two checks that needs to be that is required. So merong dalawang consideration na required in the design, no? So first is at the transfer of load. So for example, pre-tensioning ka or post-tensioning. So after that, 'di ba, i-release yung tendon, and at the moment na ito-transfer nung tendon yung stress doon sa concrete. So this is when the concrete feels the first feels the pre-stress. So ito yung bago pa siya natapos yung concrete na pre-stress concrete. So the concrete is less strong kasi hindi pa siya nag-age ng maayos, nag-age ng matagal yung concrete or nag-cure, but it is already in a hardened state na siya. So but the situation is temporary and the stresses are only due to the pre-stress. So yung pag-apply ng pre-stress na load or force, and then yung self-weight nung concrete. So hindi pa kasali yung service loads, yung applied loads, no? So hindi pa siya like for example, hindi pa siya na-install sa building or sa paggagamitan ng mga members. Now, at service or at loading, pag na-apply na yung load, the stresses induced by the service loads, in addition to the pre-stress and self-weight, must be checked. So at service stage, the concrete has its full strength, but losses will have occurred, and so the pre-stress force is reduced. So speaking of losses, so I have made you a research on what are the losses on pre-stress. So marami yun, depende sa case. But in general, pag yung pre-stress is meron siyang mga losses pag nag-apply ka ng mga service loads. So hopefully through that assignment is naintindihan yung mga losses, no? Okay. Now consider here a beam. So a beam with cross-section BD. So this is a rectangular concrete beam with span L supported by a hinge and a roller. So with service loads or distributed load na omega. So as a review sa concrete design natin, the maximum moment present in this beam is at the middle na section, no? So sa L over 2. So nandun yung maximum moment. But yung in terms of shear is doon siya sa support, no? Sa support yung maximum shear. But yung moment nandito siya sa mid-span. Nandun yung maximum na moment. So for a beam with span L with distributed load omega, yung moment natin is omega L squared over 8. So I hope alam nyo kung paano nakuha yan, no? So and then it has an area of BD, that is B times D, yung cross section niya, and moment of inertia na BD cube over 12. So this is a given already for a rectangular section. So BD cube over 12. This is a moment of inertia with respect to the x-axis or yung neutral axis natin dito. Okay, so for prestressed concrete, we have two cases. Now, case 1 is centroidal axial prestress. So that is along the neutral axis, dun ka mag-a-apply ng prestress na load. Meaning yung tendon mo is nandun sa neutral axis, and then merong na-induce na force P, that is yung prestress na force natin. So axial because it is normal to an area or perpendicular to an area, and centroidal kasi nandun siya sa center or dun siya sa neutral axis. Now, given this set of beam with loading omega, distributed load omega, so this is our section. So titingnan natin yung mga stresses na magka-create pag nag-induce ng load P at saka pre-stress force P at yung load na omega. So before we proceed, so let us note that sa our sign convention would be compression is negative and tension is positive. So first is due to pre-stress. So stresses or produced by pre-stress, and also stresses produced by pre-stressing force and stresses produced by the loading. Now, due to pre-stress, meron tayong compressive force na negative P over A. So, pag compressive, negative, okay? So, but the stress is P over A. So, simply, the application of force to an area. So, yan yung axial stress. So, P over A. So, equal siya. So, both sa taas at baba, no? So, P over A. So, uniform yung distribution ng stress within that area. Kasi, nasa center siya, sa gitna siya. And then, that is due to pre-stress. Now, due to loading, so, ano yung makikreate na stress due to this loading? So, yun, makikreate na stress is yung bending stress. So, due to the moment. So, bending stress will create a so para magka-curve siya, no, magka-curve pababa yung beam natin. So, at the top fiber, meron tayong compression, and at the bottom fiber nandun yung tension. So, that is ML or moment due to load times C over I. So, that is bending stress, or M over Z, which is Z is the section modulus, which is I over C. So, but hindi necessarily yung, para less lang yung mga units natin. So, i-denote lang natin as MC over I. So, that is the bending stress due to the loading. So, And the tension naman, of course, is equal lang sila, no? So, moment due to loading times C over I. So, C is from the neutral axis to the outermost fiber. So, that is D over 2. So, yung C natin, no? So, yung sa pinaka dulo na fiber. So, and then, so ito yung stresses na present, no? So, axial stress, P over A due to pre-stress, and bending stress, MC over I is the moment of inertia with respect to the neutral axis. This is due to loading. So, pag i-add mo itong dalawa, so magkakaroon siya ng resultant stress na compressive. So, yan yung goal ng pre-stressing na yung total or yung resultant stress induced to a beam or to a section is lahat compressive. So, may eliminate yung mga tensile na mga stresses or at least at the minimum is 0. So, at the top fiber, meron tayong negative P over A minus MC over I. And sa bottom fiber naman is negative P over A plus MC over I. So, we can denote na yung maximum stress at the top or bottom fiber ng section is negative P over A. This is due to the pre-stress plus minus MC over I. This is due to the bending stress dahil sa loading. Okay, so this is in the case of the centroidal axial pre-stress. Now, sa case 2 natin, which is the pre-stressing force is at an eccentricity. Meaning, hindi siya sa centroid natin, but somewhere at a distance E below the neutral axis. That is for the simply supported na beam. But for a cantilever, pag magpa-pre-stress ka ng cantilever, yung P natin is dun sa taas. Since yung sa cantilever, yung top fiber yung on tensile stress, subjected to tensile stress, and sa bottom fiber yung compressive stress. But this is for an ordinary beam, so we will induce force or pre-stressing force below the neutral axis at distance E. So this is the eccentricity na, that is yung eccentricity. So hindi sa neutral axis yung P natin. So somewhere below the neutral axis. Okay, so as is, compression is negative and tension is positive. So let us discuss ano yung mga stresses na naman na involved pag may eccentricity na yung P natin. So first is due to pre-stress. So meron tayong axial stress na negative P over A. So this is always present kasi P is subjected to this section. So ito, no? So P over A. So yan yung axial stress. And then meron tayong bending stress na naman. So since P is at an eccentricity, so yung effect niya doon sa if you can remember yung sa first module natin, so pag na-release na yung tendon, mag-create siya ng mag-induce siya ng force P. So yung effect niya doon sa beam is parang mag-curve siya pataas, no? Mag-curve yung beam pataas. So meaning sa taas yung tension, this tension, and sa baba yung compression. So this is the effect of the pre-stress, no? So this effect ng pre-stress lang. So that is the effect of pre-stress. So meron tayong positive moment due to pre-stress times C over I, and negative, so meaning compression, compressive stress, moment due to pre-stress C over I. So equal sila, no? Okay, so this is due to pre-stress. Now, due to the loading, so ganun pa rin. So magka-create siya ng parang i-curve niya pababa yung effect niya dun sa beam. So meaning sa baba na naman yung tension and sa taas yung compression. So negative MC over I and positive MC over I. So this is the three stresses na nandun sa beam natin, loaded with a distributed load na omega and pre-stressing force P at an eccentricity na E. Okay, so first is axial stress P over A, bending stress MC over I, and due to pre-stress, and bending stress due to loading MC over I. Now this is equals to this will create ideally a compressive force. So dapat yung magiging yun yung idea ng pre-stress. So yung matitirang stress or yung resulting stress is compressive. So that is to eliminate yung mga tensile stresses. So that is, so at the top fiber meron tayong negative P over A plus MC over I due to pre-stress and MC over I due to loading. Now sa bottom naman, FB is equals to P over A minus MC over I plus MC over I. So if you can see, sign lang yung difference nila, no? So you can create a single equation. Maximum stress at the bottom or at the top fiber is negative P over A plus minus MC over I minus plus MC over I. So pag top fiber plus minus and pag bottom fiber is minus plus. That is for a ganitong type ng beam. So pag cantilever na or ibang mga beam, so iba naman yung magiging effect. So this for a ordinary lang na beam with rectangular cross section na BD. Okay, so specific. So let us consider this beam AB with a distributed load omega with span L and a pre-stressing force induced at an eccentricity E. So this beam has a cross section, rectangular cross section BD. Okay, so before we proceed with the analysis, so let us determine yung mga properties ng rectangular cross section beam natin. So first is yung area. Area is B times D. And then yung C, or the distance from the neutral axis to the outermost fiber, is D over 2. And then, lahat kayo familiar dito, no? So, moment of inertia with respect to the neutral axis is BD cubed over 12 for a rectangular cross section. And then, the moment, maximum moment, so that is at midspan, is omega L squared over 8. So, this is moment due to the loading, due to the omega. So, na-take up na natin to sa concrete design. So, alam nyo na paano to na-derive. And then, moment due to pre-stress is simply P times E. Now, previously, our formula for the maximum stress is negative P over A plus minus MC over I minus plus MC over I. So, this is applicable for all types of beam, or like for any area or any loading or any pre-stressing force. Now, for a general sense, negative P over A plus minus. So for pre-stressing at an eccentricity, so we can say that P times C. So MP is P times C, and then Y if not the outermost fiber. So somewhere in between the neutral axis and yung outermost fiber. So general lang to na equation. So over moment of inertia minus plus M due to loading. So sa beam, iba-ibang loading. So there could be concentrated load or distributed load. So hindi natin ma-substitute itong omega L squared over 8 kasi this is only specific for a distributed loading times Y over I. Okay. So for maximum stress, negative P over A plus minus PEC. So this is because yung Y natin is naging C. So meaning, doon na siya sa outermost fiber where yung stress natin is maximum. So, maximum stress at the bottom or at the top is negative P over A plus minus PEC over I minus plus MC over I. So, that is simply, etong equation is sinubstitute natin yung Y na naging C. Okay. So, for a rectangular beam, so for this rectangular beam na cross-section, this will be the formula. So, we will substitute C with D over 2 and I with BD cube over 12. Okay? So, negative P over BD plus minus 6PE over BD squared minus plus 6M due to loading. So, depende sa magiging loading niya, no? So, kung distributed loaded na omega, so you can substitute na yung omega L squared over dito. But, in general sense, so, depende pa rin sa loading. So, moment lang ilalagay natin, no? So, over BD squared. So, ito yung magiging formula natin. If we will compute a rectangular beam na cross-section. So, without knowing yung loading, no? So, sa loading, we can solve naman yung moment due to loading. So, there could be a concentrated load na additional to the distributed load. So, depende. But this is the formula. So, we will work on this formula. So, basically, we will have more problems on rectangular beams since it is the most commonly used dito sa atin, sa Philippines. And maybe we can introduce other problems like I-beams or slabs. There are also pre-stressed na mga slabs, no? So, hindi lang beaming pre-stressed. Meron din mga slab na pre-stressed. So, we can try that. So, but for a rectangular beam, ito yung formula for maximum stress, bottom or top, no? So that's it. Okay, so we will solve problems for the next module. So these are the references. So this ends our module 2. So thank you for listening and have a good day.